I am on the list. Okay, that's great. Um, Memory reduction, which is my most recent thing, so hopefully more fresh in my mind than other stuff. So this is the very rough diagram of of the online architecture. So you've one cool WSD, you've many kits, and you have one fork kit, and your fork kit's job is to make kits. The point of this is that when it comes to memory reduction, if cool WSD accumulates memory, then it'll be around for a long time. If an individual kit accumulates memory, it'll last for a shorter period of time. So there's a difference in kind of the impact. On the other hand, a kit will uses up a lot more memory, typically than cool WSD. So some kind of general architecture there. And then on the actual difference between a fork kit and a kit is that in all cases, a kit is basically a LibreOffice instance, and a fork kit is LibreOffice initialized up as far as when you would load a document. And then what happens is that you're using the fact that Linux does copy and write to take your fork kit at this pause before it opens a document state, and you clone it for every individual document you open up, and you're hoping that the new kits will share as much as possible from that fork kit, so that each individual document takes a small amount of memory, and that it's sharing what it's inherited from this one in between. Which means that when you're trying to save memory, you're doing a few different things. You are trying to maybe find out where you copying memory. Why is there memory being copied when you're between the original fork kit and the kit? And if you can avoid doing that copy in the first place, is there things you're touching that you don't need to touch? Then there's cases of when there's things that a kit is allocating that maybe you've got every kit is allocating the same thing, and you can move that to the parent fork kit and you only have to allocate it once, and then you can share it. And then there's cases of where you're just allocating memory that you don't need, and can you avoid that? And then that outside of those kit and fork kits, back up in cool WSD where you have this long-lived memory, can you reduce the amount of memory there? And in general, can we just identify what is doing what, and what is the memory we have in mind? So with this fork kit, we have the preload data where we try to load up everything in this one case so that all of the other kits will inherit it. So you're trying to make sure that everything that will be used eventually happens in the fork kit. So the obvious ones we have is spelling dictionaries. We know you're likely to spell check. We know you're likely to hyphenate. You might use the thesaurus. You'll definitely have the icons in the sidebars and the user interface. All those are going to be loaded anyway. So we insist that they're loaded in the fork kit once, and then we're hoping to reuse the copy of all of that in the individual kits. So the first kind of approach looked at more recently was to have a look at the differences between your fork kit and your kit and see where are there things being copied by that kit that we did not expect to get copied, that we assumed that the original fork kit copy would be left alone and it wouldn't require changing. And the approach we're using here is to use Linux's perf. We try to find out what thing does a kernel call when it does this copy and write, and it's this WP do WP page thing. You can write a perf, you can inject a perf probe for that as written there, and then you can visualize as a flame graph, as we've seen during the last few days, as to get an overview of what is being copied when a kit is being created from a fork kit. And we look at the widest one. And I've just zoomed in here to one of the widest ones. And we can see that we've got some configuration stuff going on here. And we see that this is just the stuff that has been copied. So we've got some stuff that's been copied here. It's in the configuration. We know that we've actually pre-loaded all our configuration. So we expect that there should be no reason at this point to do any modifications to the configuration. It is, so perhaps the document had just started. The first assumption is maybe there is some writing to configuration going on by something that decided that it's going to be different. Why is it copying? We don't know initially. We have modified this configuration so that it should not be modified just by the sheer fact of looking at it. If you increment the reference count, decrement the reference count, there should be no modifications going on there. And there's just one branch of this whole configuration manager thing, which is just missing that optimization, which goes unnoticed unless you can be able to visualize what is going on and being able to look at the full picture of what copying is going on. So this small, in the overall scheme of things, adds up to about 2.8K per document just in this copying. And the little issue is that these are the localized configuration names. The names of the localized options adds up to about 2.8K per doc. So that's identifying things that were copied which shouldn't be copied. There's more of them, but that's just a sample of that to take advantage of copy and write and to discover when it's happened, when you didn't want it to happen. The other obvious approach that I said earlier is just to find things that every individual kit allocates, and if every kit is allocating the same thing, this looks like an obvious candidate of something that should have been allocated once back in the parent kit. The approach I've used in here is just to reuse Google's TC-malloc, which has some ability to trace where allocations are coming from, and it makes some use of that, and then use a flame graph again to visualize where are most allocations happening in a freshly created document. So you get this wall of allocations, and if you zoom in on them here, we can look at some of them later, we'll go through 2 or 3 of them. But just the point is that you can see what has been allocated in a freshly created document. You can click on it, you can zoom in, and obviously the wider something is, the more significant it is, so you can just go straight to the wide ones and not worry about smaller ones. So if we zoom in on one of those, we're seeing here is in the sidebar at the bottom, the second last line that's visible, you can see it's sidebar toolbox. The sidebar toolbox is inserting graphics into the sidebar for the icons, and it turns out that the sidebar uses up quite a few icons, and this is not a path that's part of the preload that we have done for all the other icons. So we're just missing a case of load up the icons in the sidebar that we're likely to use. So we just add this into the list of things in the preload that we allocate. Every one of the, now the fork kit loads these up, and the individual kit copies don't have to have their own one. So you've gone from however many kits are loading it, all of them, 50 at a time simultaneously perhaps, to just having one single copy in that fork kit parent. The best type of allocations are the ones that you don't need at all. And again, if we go back to the original list here, close to the right hand side where you can just about see some text, you can see 2 tall bars there. So we're just zooming in on those 2 tall bars there. Each bar is a list, the font lists. You have 2 font lists when you look in Collaborative Line. Typically you have one on the top bar and one in the sidebar. Each one of those is one of those bars. And what it is doing is it's going through all of the text that you may show in the combo box, finding out how wide it is, measuring the glyph widths, caching the glyph widths for use later on, using that to determine what's the widest string. And it doesn't actually matter because those 2 combo boxes don't use that information. They just decided that the width of a combo box is 150 pixels or something, and then it draws a picture of the font, and it draws a picture, and the pictures are what are actually shown, none of the cached glyphs and all the rest of it. So, you don't need that. So it's a 1-line fix that says if you're in user draw mode, which is what that is, don't cache the glyphs, you're not going to use them, and you get whatever that is, the 2 megs, depending on the number of fonts. For me, the number of fonts I have, it's 2 megs per document. So those there kind of add up to, for my case, with those mentioned examples, about 5 megs per document. A writer kit is about 50, so you're looking at about a 10% saving in memory with the mentions there per at the kit level. Moving up then to CoolWSD itself, you can use the same techniques with TC-malloc and dumping out the profiles to find out what are your live allocations. And I was looking generally at live allocations and not allocations over time, but that is also a factor because once you allocate something, the program tends to hold on to it. So if you allocate 7 megs and you release 4 megs, your footprint is still that original 7 megs. So once you start allocating a lot of things, you're generally stuck at that high water mark outside of special cases where you've made an exceptional allocation, which was, we'll forget about that, but generally you're stuck with the high water mark, which means that if you have, in this case, the very, very first initial startup of CoolWC, which loads up all of the documents that it will serve out later on, all of the HTML documents and whatnot, loads them all up, and it does that in a certain way that it uses a lot of memory temporarily for that process, that when it actually then settles and it's finished doing its initialization and has allocated, 100 megs or 200 megs to do that, and then afterwards it only needs 5 megs, it doesn't matter, it still has a footprint of, that 200 megs. But by using the same technique, you can find out where are your allocations. This is just a freshly started CoolWC. It hasn't done anything except load up the HTML files it'll serve out later on. And what you can do there then is you've got two levels of things that are using up memory. You've got the standard map is using more memory than you expect, and you can do things like shrink that down. And then the actual allocator itself, the malloc level, has also allocated memory that it refuses to return back unless you force it to. So two things: you can shrink at the explicit programming level that you want this to be shrunk down to the size it needs to fit, and then you can ask malloc, similar ones, malloc trim, to just explicitly return the memory they're not using back to the server, which means that the initial startup right now of CoolWC will use a significantly less memory than it did in the previous major release. So you get that win going on. And because of that find as well, we've also more regularly are using the malloc trim to return back to the operating system memory that we're not using. So you should see a kind of a more realistic quantity of memory being used by the standard operating system memory using tools. They should be more realistic. I suppose another win, and I'm coming close to the end, another win here is the admin documents. If you're going into the admin page in Collaborate Online, it'll tell you what documents have been loaded up in the past, and while they're open, it'll update them as to how much memory they use, how long they've been open, things like that. Once a document is closed, it'll then show you the historical data on how much memory each individual document used while it was open. But once they've actually been closed, those numbers don't change. So rather than keep all the large structure that we were keeping of all the documents that we had ever opened in the past, we know we're only going to use them to be reported as a simple string. So output that as a simple string, throw away all the complicated structures, and now all of the historical documents are just a string, not a gigantic tree of data that will be dynamically updated. So it makes a difference over time. The longer your CoolWC instance is up and running, the more of an impact this change makes. So if it's up for 5 minutes, no change. It's up for 2 or 3 weeks. The steady deterioration of loss of memory from this aspect is finished. It's complete and not an aspect anymore. What was in progress at the time of writing this slide has been 50% of it is merged. It's just an observation that similarly, as I said at the beginning, where if you use a lot of memory for a short period of time, you're stuck with the cost of that over a longer time, is that we identify places where we are accumulating large amounts of data in buffers and operating on that massive block where we could instead do it in little smaller parts. Clipboards are a good example where, especially when you have large images and you select a large image and you copy it around the place, they balloon up to very, very large sizes. So rather than copy them around in huge memory blobs, either we try to save them as files and we hand off just the file name itself when we're moving between that CoolWC and individual kits, or when we're moving from CoolWC down to individual browser, that we're trying to serve them out as small chunks that your browser will pull down piece by piece, rather than trying to read them all into memory at the CoolWC side and then having them there in this massive buffer until the browser's finished with them. So it's just a change of approach to try and identify what things are bloating up in memory, what the reasons are for that, and then identifying whether the approach is to, at a kit level, move the allocations around the place, shrink something because it doesn't need to be that big, or generally at the cool WSD level, can we be more smart about how we use our memory so that we don't get these massive peaks and troughs and just get a more flat line, consistent approach. And that's it. Thank you.